হ্যাঁ, ও বলতে পারো মানে একজন তোমাদেরই মতন একজন ইয়াং স্টুডেন্ট রিসার্চার, যার ফলে আমরা ওকে ইনভাইট করেছি যে এই টকগুলো দেওয়ার জন্য। ও এক্সোপ্ল্যানেট নিয়ে কাজ করে এবং বিশ্বভারতী ইউনিভার্সিটি থেকে ও ইন্টিগ্রেটেড মাস্টার্স ইন ফিজিক্স উইথ স্পেশালাইজেশন ইন অ্যাস্ট্রোফিজিক্স করেছে। করার পরে অ্যাট প্রেজেন্ট ওর এবং ডিউরিং মাস্টার্স ওর কাজ ছিল এক্সোপ্ল্যানেট নিয়ে স্পেশালাইজেশন প্রজেক্টে। অ্যাট প্রেজেন্ট ও রয়েছে ইন্ডিয়ান ইনস্টিটিউট অফ অ্যাস্ট্রোফিজিক্সে অ্যাজ আ প্রজেক্ট ফেলো। গত প্রায় 1.5 বছর ধরে ও প্রজেক্ট ফেলো হিসেবে থাকার ফলে একটা রেয়ার কাজ ও করতে পেরেছে, যার ফলে আমরা ভেরি মাচ হ্যাপি। যেহেতু মানে ওয়ান অফ দ্য ভেরি ফিউ প্রজেক্ট স্টুডেন্ট হিসেবে পেপার পাবলিশ করা ইজ ডিফিকাল্ট, বিকজ পেপার পাবলিকেশন ইন আ গুড জার্নাল এটা একটা কমপ্লিটলি ডিফারেন্ট গেম। হ্যাঁ, কমপ্লিটলি ডিফারেন্ট টাইপ অফ ডেডিকেশন তার জন্য লাগে। তো ও কিন্তু গত 1.5 বছরে এই এক্সোপ্ল্যানেট স্টাডিজ এর সাথে যুক্ত থাকার সাথে গত কয়েক মাস আগে এক্সোপ্ল্যানেট হ্যাবিটেবিলিটি নিয়ে ফার্স্ট অথার পেপার একটি দিতে পেরেছে, যেটা ইজ আ ভেরি রেয়ার অ্যাচিভমেন্ট বিং আ প্রজেক্ট স্টুডেন্ট। যেহেতু ওর কাজ এক্সোপ্ল্যানেট নিয়ে, আমরা চাইবো যে ও এক্সোপ্ল্যানেট সম্পর্কে দুটি ক্লাস ও আমাদের নেবে। একটা হচ্ছে আজকের যে ক্লাসটা, যেটা টিসিয়া বললো যে এক্সোপ্ল্যানেটস এর ডিটেলস, বেসিক্স অ্যাবাউট এক্সোপ্ল্যানেটস, সেটা হয়তো কেউ কেউ তোমরা একটু অলরেডি এর আগেও হয়তো কোথাও পড়েছো বা দেখেছো। আর আগামী কাল আমরা একটু হাইলাইট হবে যে এক্সোপ্ল্যানেট সায়েন্স নিয়ে ইন্ডিয়া থেকে কি রিসার্চ হচ্ছে, কিভাবে হচ্ছে, কেন হচ্ছে, সেই নিয়ে। তো এই দুটো ক্লাস অন এক্সোপ্ল্যানেটস আমাদের সাথে টিসিয়া গুপ্ত পাইন ওই নেবে। ওয়েলকাম টিসিয়া, তুমি জয়েন করেছো বলে ভালো লাগছে। অ্যান্ড আমি মনে করি যে তোমার এই টকগুলো তোমার থেকে যারা একটু জুনিয়র ইয়াং স্টুডেন্টস তাদের জন্য এটা খুব মোটিভেটিং হয়ে যাবে। থ্যাংক ইউ। থ্যাংক ইউ।
Yeah, thank you for so much for having me. So I'll keep most of the presentation in English, and of course I'll also switch between Bengali as well. So before we begin, the entire concept of exoplanets has been fascinating us since a really long time, right? We all have read sci-fi. We all have read Satyajit Ray's like Bonku Babur Bondhu, and we have watched ET, and this entire domain of extraterrestrial life and other planets, so as to say, has been fascinating us for a really long time. But the problem was that detecting these planets in particular is not that easy. Detecting these planets had to go like, in order for us to detect the planets in the first place, we had to go through a huge number of procedures one after the other. And after going through all of those, after figuring out all the caveats, we finally were able to detect the first exoplanet with a confirmed uh, domain with a confirmed domain of confidence in the year 1995, and that was done by Michel Mayor and Didier Queloz. Now, I'll move to that in a short while through the slides. But before that, I just wanted to appreciate the fact that how the human curiosity itself has been able to think of something like this, and actually has strived in that direction to actually go ahead and detect it. So, without further ado, let us start with the human curiosity itself. The first questions which we had. So, have you ever looked up at the sky and wondered, like, is somebody out there? And are there really other worlds around those stars, around those countless millions and billions of stars which you see in the night sky? And if there are planets around those stars, what are they like? And can we maybe go and live and
কিশোর অডিও ভিডিও দুটোই পজ হয়ে গেছে।
হ্যাঁ
about how our solar system was formed,
টিসিয়া,
how our solar system would
ওকে।
evolve, and
না না, ইটস ওকে, ইটস
হ্যাঁ
ওকে। হ্যাঁ, অডিও ভিডিও পজ হয়ে গিয়েছিল, ঠিক আছে, নাও ইট
hello.
ইজ ওকে। ইয়া, হ্যালো হ্যালো। ইয়া,
Oh, okay.
ওকে, নাও ইট ইজ ওকে।
হ্যাঁ
ইউ ক্যান
ঠিক
ইউ
আছে।
ক্যান কন্টিনিউ। ইয়েস ইয়েস।
হ্যাঁ হ্যাঁ, এবার ঠিক আছে। আমার একটুখানি ইন্টারনেটটা
ইয়েস
ফ্লাকচুয়েট
ইয়েস
করেছিল।
ইয়েস 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 ইয়েস, নাও ইট
হ্যাঁ,
ইজ ওকে।
এবার ঠিক
নাও
আছে।
ইট ইজ
ওকে।
ইয়েস। হ্যাঁ।
এবার আমি কন্টিনিউ তাহলে। জাস্ট সরি 1 মিনিট, আমার আবার একটা ফ্লাকচুয়েশন নেব। হ্যাঁ, এবার ঠিক আছে তো?
ইয়েস ইয়েস ইয়েস
Hello?
ইয়েস ঠিক আছে, ইয়েস ইয়েস একদম, ইয়েস ইয়েস ইয়েস,
Hello?
ওকে, ইয়েস ইয়েস, হ্যালো,
Yeah.
হ্যালো, হ্যাঁ, ইয়েস ইয়েস, ইউ ক্যান কন্টিনিউ, ইয়েস।
Can you? Okay, perfect. Okay, so yes, so these worlds tell us also about our solar system, how we can actually test the theories which we have regarding planetary dynamics by actually observing the things. So, and finally, we can also confirm whether there are some truth to the science fictions that we are so familiar with. And one of the major questions being, can we find Earth-like planets out there around other stars? And the one of the motives of finding Earth-like planets, other than the fact that we might go and maybe live there someday, is can there be the possibility of life elsewhere other than on Earth? So now the question is, how do we approach in answering these questions? Now, science is based upon very strict logic. You cannot really deviate from logic and do anything else. So whenever we try to understand or explore something, we must remember that it should not only explain what new we are observing, that same thing should also be applicable to whatever has already been observed. So, to understand why this is important, we first have to acknowledge that fact that exploration in itself is a fundamental trait of living beings. And I'm not just limiting it to humans. As living beings, each and every life form has to explore around its environment to look for food, to look for safety, shelter, etc., etc. And then, of course, humans have knowledge as their distinctive trait. Knowledge is something which is particular to humans. And finally, what I would like to highlight on is the fact that astronomy in itself is the ultimate laboratory for physics. Anything that you can think up, if you want to actually test it, be it a gamma ray detection or some particle experiment which you have in mind, even if you cannot make it on Earth, you can use astronomy to actually observe stars, observe extreme environments around them, and detect those. So, understanding how to detect these new worlds outside is what we need, is what we are going to focus on this talk particularly. So, the first detections are radial velocity and transit, which we are going to cover soon. And then each of these detections themselves had technological challenges, which is why we were not able to detect them, even though they were theorized, they were thought of, and they were scientifically like logically channelized way before the first exoplanet discoveries happened. And essentially what we have to realize here is that whatever we do, we have to base everything on knowledge. And that knowledge should always lead us in a logical pathway to what we are going to find. So, of course, the bottom line of everything is, again, can we find Earth like planets? And if so, can life be there? As of now, we do not have any life outside Earth. Earth is the only place in the entire universe where life exists. So before I move on to the detection methods and a brief history of how exoplanets were found in the first place, let us first quickly understand how we build our knowledge based on what we know. So as I said, everything goes on step by step. We build on stuff. So what do we already know about the solar system? We already know that there are Earth-like planets, as in Earth, Venus, Mercury, and Mars. Right. And then we have Neptune like planets, such as essentially Neptune and Uranus. And then we have gas giants, or so as to say Jupiter and Saturn. Okay, but we don't really have super Earth. Would anyone like to try and guess why do we have a super Earth category for exoplanets as well? We don't have super Earth, but what do we have in our solar system that allows us to think up super Earth? Or rather, let me phrase it in this way: what do we not have in our solar system that allows us to think that okay, there could be a super Earth? Anyone? You can unmute and answer. No one, no takers. You can unmute and answer. Like, it's fine to be wrong. It's completely okay. Yeah, but that's an exoplanet. What my question was that, like, even before, let's say you detect a new exoplanet, you are categorizing that exoplanet as super Earth. Yes. See, good. This is what I essentially want you to do. Like, this is how we thought about this. So, what we realized was, okay, we have Earth like planets. And then straight away, we have Neptune like planets. But there are some planets where we see that the size of the planet is, it's not as small as Earth, but then again, it's not as big as Neptune. So we need something in between. So, yes, Earth like planets, but bigger in size. And since they are Earth like in that sense, super Earths have a similar density to that of the planet Earth. So, yes, that is how you build up on the logic. So, now let us come to the main focus of today, which is exoplanets and their detection. So in the background, what you see here is all the different kinds of space observatories and ground-based observatories, which were, or I mean, space telescopes and ground-based observatories, which were used in all these years to detect exoplanets. So now the first exoplanet, which was discovered and confirmed, and which went on to win the Nobel Prize in Physics, was Pegasi 51. Pegasi 51b to be specific. It was a Nature paper published in 1995. It won the Nobel Prize for Michel Mayor and Didier Queloz. On this one, this is Michel Mayor, and this is Didier Queloz. So now, the fun part about their journey of detecting a planet through radial velocity is that they already had the data in a sense. But the problem was, whenever you have any astronomical data, I think by now you all have a rough idea of this, that whenever you have any astronomical data, you have to make sure that the data is not noisy enough, which means that just because you have a data does not mean it's error free, right? It has lots of error. But now the question is, how much error are you willing to trade off? So let's say I have let's say I have a circle, and in that circle I want to measure a very small portion. Let's say there are 100 points in a particular circle. Just imagine a circle. Okay, let's start drawing. Imagine a circle, and let's imagine that within this circle you have 100 points, precisely 100 points. And let's say out of these 100 points, you want to detect 10 points, a very small region of the circle. You want to detect 10 out of these 100 points. Now, if your detector, uh, okay, I'll come back to this. So now let's say your detector is such, it has such a sensitivity that it will give you a plus minus range of 10 points to begin with. Now the question is, even if you do detect something, how do you convince the community or even yourself that whatever you're detecting is true? So now, but if you can make an instrument that tells you that whatever you are detecting is within an error margin of plus minus 1 point, then you can say that, okay, whatever this 10 point I'm detecting, since it's within the range of plus minus 1, it is a valid detection. So this was the main problem why people could not actually use the radial velocity to detect a exoplanet around a star till 1995. Now let us understand how this happened precisely. So this is the radial velocity method. So in a very easy sense, all of you have played Ringa Ringa Roses, right? All of you have played games as children. So whenever you hold your friend's hands like this and you spin them around, do you also realize that you're also going in a small circle? Like, assuming that you are the heavier friend. So whenever you hold hands and you tug each other and you go about in a circle, what happens is that it's not that just one of you is moving. The other one is also moving, but in this case, of course, it's a star and a planet. So obviously you would not expect the star to move as much as the planet. like you see in the case of binary stars. In binary stars, two stars could be roughly of the same mass and they have a barycenter around which they go round and round. But in this case, it's a planet. It's a very small mass, which means that the star is hardly going to be moved by the planet. But nevertheless, point being, the star will move around a certain common center, which could be inside the star, but it will definitely move. So we call this movement as a wobble. WOBBLE, wobble. So what the astronomers tried to do was detect this particular wobble in their systems in this particular fashion. So what did they do? They took the advantage of Doppler shifts. So when I say wobble, it means if the star is here, the star is just going to put very small motions which basically go towards you and then away from you, towards you, away from you. And as the star is going towards you, the Doppler shift is going to shift it towards the blue wavelength. And then as the star moves away from you, because of Doppler shift, it's going to get red shifted. So what they realized was, if they use Doppler shift, and if they can essentially understand how to get this and this over a certain period of time, and they plug it into the equations of what we know about simple harmonic motion, and then obviously this is only possible through spectroscopic observations, and obviously they need they need a high resolution for the spectroscopic observations, and a little bit of innovation to realize how to bring this method to life. What you essentially have is an exoplanet detection. So by measuring the wobble of the star, by taking the star's spectra over a long period of time, you see the spectra shifting towards the red, towards the blue, red, blue, red, blue. And this shift towards the red and blue is periodic. Because why is it periodic? The only reason it can be periodic is if there is a planet going around it, and that is how you have the first exoplanet detection in 1995, and it gives you a Nobel Prize. Now we come to transiting planets, or the transit method of planetary detection. So transit method is kind of simple. In fact, so would any of you like to like guess how it more or less works? I think more or less everyone is familiar with this particular method. As in, so essentially you have a planet crossing across a star, and then there's a dip in the starlight. But the question is a simple question. Can you see the shadow of a planet when you're observing a star? What do you think? You can write yes or no in the chat box. Let's say a planet is crossing in front of a star. The star is some parsecs light years away. Can you see the shadow? See as in, can you actually see the shadow on a photographic plate or with your eye or anything? You can write yes or no, whatever, like what your opinion is. Okay, I get one no. Anyone for yes? Anyone wants to go for yes? No? All right. Any other answers? Okay. No so far. Good. So obviously you cannot see the shadow of the planet with your own eyes. And you cannot really even see the star flickering or anything, because the amount of light which is blocked by that planet is very, very little. So what can you do? You can measure the luminosity of that particular star through your detector, and then see how much of that luminosity is getting dropped for what period of time. So now this transit method turned out to be a huge hit, because there are loads of things that you can do with this transit method. So right now you can see just one planet transiting this particular star. Let's say there is another planet which is transiting. Let's say another planet is transiting from here. Even in that case, now this is the beauty of the transit method. You can actually detect multiple planets transiting a particular star. In a more clearer picture, let me show you here. Let's say this is your star, and this is your first exoplanet that is transiting. And then you can have another exoplanet which will transit in some time. It hasn't started transiting yet, but it will transit in some time. So as this first exoplanet is transiting, you get the light curve. If this was a single exoplanet transit, this would be your light curve. As this second one approaches, let's say the first one has gone here and the second one has just entered here, you will see a second dip. And as this first one finishes the transit, it will again go back to here, whatever this particular initial depth was, and then this will again go back to the normal starlight. So what we have here essentially is that we have actually modeled two planets transiting over a certain period of time, and given the time each planet took, we also could understand where that planet is located, which means that what we essentially did was figure out what was the orientation of the star planet system itself. What does that mean precisely? It means that now if you know the technique of transit, and if you know the technique of radial velocity, this is what you can do. So if you know transit, it gives you the transit depth. The transit depth gives you, so this transit depth is equals to rp by r star whole square. What does that mean? Take the root of the transit depth. You already know radius of the star. You find the radius of the planet. So transit gives you the radius of the planet. It gives you the time the planet took to cross in front of its star, which means it gives you the orbital period of the planet. And if you also observe that particular planet by radial velocity, you find the mass of the planet. So this part is kind of straightforward. If you have a big planet, the bigger planet is going to tug at the star more forcefully than a smaller planet. So if you see a high redshift and blueshift change, which means the star is wobbling strongly, it's a massive planet. If the star is wobbling relatively less stronger, it's a less massive planet or a smaller planet. So if you have the measurement of mass and if you have the measurement of radius of a planet, what you essentially have is the density of the planet now. Obviously, you assume that the planet is spherical and you plot it, like you feed the numbers into the equation and you get the density of the planet. So once you start getting into the density of the planet, this is where things get interesting. Now you can understand why and how rather we can classify a planet into Earth-like, into a super Earth-like, Neptune-like, or Jupiter-like. Because the solar system planets are very well studied. And therefore, what we do is try to essentially compare everything, whatever we find, with the solar system. We will come back to this again after a couple of slides. But so far, this is how we proceed. Now, the other thing which I would like to also highlight is the chain-keeping relations, which is often used in exoplanets a lot. So now, what can happen is that, let's say you observe a transit, but it can always be the case that just because you observe a transit of a planet, you might not just observe the radial velocity as well. So you observe the transit, but you do not have any data for radial velocity. What does that mean? That means you have the radius of the planet, but you do not have the mass of the planet. Or it could be that you have detected a planet's radial, like you have detected a planet with the radial velocity method. You know how strongly the star is wobbling, hence you know the mass of the planet. But you do not see the planet transiting. And how can that be the case? Because, okay, can someone tell me when would I not see the transit of a planet? You can switch on your mic and answer as well. Just think about it for a while and tell me when would I not observe the transit of a planet. Let me go back to the last slide. When would I not observe this transit? So this is a star. This is a planet going around it. this is your plane of view. You are observing this planet going around the star. The question is, when would be the case that you do not observe a transit around the star, which means that you cannot really detect if a
When
planet. Go on.
the angular momentum vector is towards us.
Sorry.
When the angular momentum vector towards us, dx towards us.
Yes. So when the angle of the orientation of the planetary system is like tilting towards us. Very good. Correct. That is precisely the answer. Yes. So which means that if the orientation of the planetary system was rather this, if let's say the orientation of the planetary system, so this is the star, this is our star, and if the orientation of the planet orbiting the star is somewhat like this, then you see that the path of the planet is entirely missing the face of the star with respect to our orientation, which means that in this case we cannot have a transit detection. That does not mean that we cannot still detect this planet. There are other ways, there are numerous other ways by which we can still detect it, but transit detection won't happen, which means that we will not get a beautiful number which describes its radius. That is all. So since we can have all these cases where we can
Tisha,
detect
may I ask a
either the
question?
mass or.
Tisha, may I ask a
Yes,
question?
please.
It may seem
Yeah,
silly,
yeah, sure.
but actually, the previous case that you were showing, when in our plane
Hmm.
of view, the star is basically revolved by
Hmm.
the planet is revolving around the sun perpendicular to means
Hmm.
in our plane of view. So in that
Yes,
case,
yes.
can we have the radial velocity method so that we can see the star
Yeah,
moving
yeah.
from its. Uh-huh. So would that
I
be
mean,
useful? Would that be useful?
yes. So, like, can you rephrase your question a bit? Like, okay, so if I'm getting it correctly, you're
Mhm.
asking that would it be useful if we measure a particular star both by transit and radial velocity, right?
No, in that case, when you are not observing the transit, when you are
Okay, if
not
we do
observing
not
the
observe.
transit,
Hmm.
transit method is not applicable. We cannot have
Oh.
red shift and blue shift, etc., etc., or we cannot have the dip in luminosity. But in that
Hmm.
case, can we detect the radial velocity of the star? And
Yes.
can that be
Yes.
used back to for exoplanet?
Yes.
Okay.
Yeah, got your question. So you were saying that let's say a star and a planet exist and we
Huh?
cannot detect them by radial velocity or transit, right?
No, no, no. We cannot detect it by transit, but can
Okay.
radial velocity method be used?
Oh, yeah, yeah, definitely.
I can understand that the star is radial velocity is coming into play as because the star is being orbited by a planet. So I
Hmm.
cannot see at first. I cannot see the planet from this
Hmm.
distance, but by the radial movement of the star,
Hmm.
can we have an idea that it is being orbited by a planet? And can we
Hmm.
find that yes, there can be some means to use the radial velocity method to find whether it is that exoplanet kind of thing or not?
Yes, yes, that
Huh,
is what we do actually. So, okay, to
huh,
precisely answer your question, what we do is we don't observe just one reading. We observe multiple readings
hmm,
for any given technique. So, even for transit or for radial velocity technique as well,
hmm,
we don't just observe it once. We observe it at least twice or thrice
hmm.
to reach the required confidence level before we confirm it as a planet, which is why you will actually find a couple of radial velocity observations marked as controversial, which means
Okay,
that you cannot have a which means it does not have a proper confidence, or it was previously detected and it does not have a newer detection. So
okay,
these detections keep on happening one after the other. Like, we keep on detecting them, and we make sure that whatever we had detected is also being detected now as well. So one of the other goals of exoplanet science right now is also to make sure that we do not have any controversial detections. And if we do not detect something, we need to make sure that it is marked as controversial.
Okay,
So
okay, I get it.
that is
And also there is another question in the transit depth in the current slide which you are showing. The transit depth is basically RP by R star. RP is the radius of the planet, and R
yes,
star is that of the star. So
yes,
basically, is it related to how much area, if we consider them to be circular, how much area of the planet is being blocked, of the star is being blocked by the planet, which may appear what we are seeing from us from this point, it is basically a kind of circular area. So how much circular area of the star is being blocked by the circular area of the planet? Is it related, the transit date related to this thing? Ratio of
yes,
areas.
yes, 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 yes.
Ratio of areas.
It is precisely related to that. So
Okay.
if I were to derive it in some sense,
Mm-hmm.
it what would happen was essentially it's pi r square for the area of
Yeah,
planet.
yeah, yeah, yeah. I
Yeah,
understand. That
yeah,
is the
yeah.
ratio of the areas.
It's
Ratio of
essentially,
areas.
yeah, ratio of
Okay.
areas, because
Okay.
so what's happening is that the transit depth is being created by blocking a certain amount of light.
Exactly.
So let's
Exactly.
say,
Exactly.
yeah, yeah. So
Uh,
essentially, let's say we have 100 photons being received by the star on
huh.
our telescope,
Huh.
and let's say a small Earth-like planet is passing in front of it.
Exactly.
So
I
out
get
of,
it. I get it. Okay.
yeah,
Okay. Okay.
so
I
out
get it.
of those, let's say, yeah, 100 photons, 8 photons are getting blocked by this planet
Exactly.
in
Hmm.
that sense.
Okay.
So
I
these
understand.
8 photons become our transit depth, and
Uh-huh.
hence root of transit depth
Uh,
becomes the radius.
and the transit depth is supposed to remain constant for a given period of time when the
Yes, that
planet is
is,
moving over the stellar body.
yes,
Okay. Okay.
yes.
Okay. Okay.
Now,
Got
obviously,
it.
there are some slight caveats to that, because as the planet is slowly entering like, it's
Yeah.
slowly crossing in front of the
Uh-huh.
star.
Uh-huh.
Only a part of the planet is first entering, and then the
Yeah.
entire planet comes in.
Uh-huh.
So it's not exactly a straight drop.
Hmm.
It's more like this. It comes like
Yeah,
this,
yeah, 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 I understand.
flat, and then
Okay,
goes like
uh-huh.
this.
Very good, very
So
nice.
we have
Mm-hmm.
modeling softwares which essentially model this particular light curve,
Mm-hmm.
and that is how we essentially get the properties of the exoplanet
Okay, okay, very
one
good.
by one.
Thank you, Tisha.
Yeah, thanks for asking. Okay, so so moving on. So bottom line with the chain keeping relations is that if we know either the mass or the radius, with the chain keeping relations, we can estimate the other, and it might be the estimation might not be as solid as what we might have observed, but it gives us an idea on what to expect. However, as I already said, it we are not exactly limited by just these methods. We also have discovered many other methods of exoplanet detection, out of which I will discuss only two more, because like there are a plethora of ways you can actually detect an exoplanet. And what I want you to take away from this is what are the other two methods which are the most popular ones right now, and one of them being microlensing, gravitational microlensing to be specific. So the reason I want you to understand what gravitational microlensing is because in the next within the end of this decade, probably either within the end of this decade, like at least that's what I got to know from discussing with my professors and collaborators, and all, like we expect to detect our first exomoon, which is a moon orbiting around an exoplanet. It is sort of expected that it will happen by the end of this decade, like within the next 10 years or so. Like we will be able to use this technique of macrolensing to detect the first detection of exomoon, which will essentially open up another host of new possibilities for like life elsewhere in the universe, as well as exoplanetary dynamics and how we study exoplanets fundamentally. So my microlensing, or specifically gravitational microlensing, actually uses the general theory of relativity in observational techniques. So what we essentially look for is a blip in the data, and to properly explain, this is how it works. So for microlensing technique, what you first and foremost need is a very bright background, a very bright background. Now, who can tell me quickly where do we find a very bright background instantly in the sky? Okay, I'll come back to the drawbacks later, Spandan. Okay. Who can tell me where can I look up at the sky in a very, very clear night and find a very bright spot or a very bright patch of sky? What in where should I look? What should I look towards? Where will I find
on a new moon day, I suppose.
Hmm?
On a new
Yeah,
moon day, I suppose.
yeah, yeah. So like other than an yeah, precisely. Like making sure that there is no moon. Yeah. Hmm. No, not the moon. Like think about in terms of stars. Where will I find a really nice bright background to look towards? I'm giving you the hint. It's a background, which means it's like 8 kiloparsecs away from us. It's very, very away from us, but at the same time, it's a very beautiful, nice strip of bright stars, and like it's a really nice strip of bright
The
stars.
Milky Way.
Yes, yes, precisely the Milky Way, and like yes, correct, Rahul. So yes, so the particularly the central portion of the Milky Way galaxy, that becomes a really good portion to make these microlensing observations. The only drawback or the tricky part of this microlensing observation is the fact that so this is how the microlensing observation happens. You have a star, and around that star, a planet is going round and round. So let's say this is the star, this is the planet. You know that the star is moving across uh, like it's moving across the galactic plane, right? It's going round and round the galactic plane, so it's essentially moving across the bright background of stars. So if this bright background, if this is your Milky Way, then this, let's say the star is just moving across this bright patch of stars with a planet companion. Now what is going to happen is, as it is moving across, if it was just a single star, then this is what you would get. Since so let's say there are two stars here and here, and as this particular star passes in front of these two stars, what you will see is that the light from both of these stars will be lensed. Rise in the brightness and then a gradual fall because it is again moving out of your view if in the case of a single star. But let's say you have an exoplanet around that star. This small blip that you see here, it's an extremely small blip, and it required us to essentially probe into very, very fine levels of detection to actually get that small blip, which tells us that okay, this small blip can only happen if there is an exoplanet around that star. And this small blip is the result of gravitational microlensing, which means that the light, because of the stars and the planet's gravity, the light is getting bent in a very small fraction. And it is that small bend of the light that we get as that small blip as the star and the planet move across this huge patch of white stars, which fills your night skies, as and you call it the Milky Way. So this is essentially the technique of microlensing, and in IIA we have the Indian Astronomical Observatory in Hanle, and that is where they are essentially trying to get this microlensing technique to make it fine enough to detect exomoons later. And so far there have been some detections, as in there have like you can use the Indian Astronomical Observatory in Hanle. You can use the telescopes there to actually get microlensing observations. It does have that power in it. So that is what some of the people here in IIA are trying to do as well. And then we move on to
Acha, Tisho,
direct imaging.
Tisho,
So direct imaging is something which my own
Tisho, can you
professor
hear
is
me?
working as of now. Yes.
Can you hear me?
Yeah, yeah.
Oh, just
Yes,
move to
yes.
the previous slide. Just move to the previous
Hmm.
slide. As far as I can understand, there is a dip, there is an increase in the brightness,
Hello?
as because can you hear me? Am I audible? Am I audible?
Yeah, now it's okay. Now it's okay.
Okay, okay.
Yeah, now it's
Let me understand this diagram first. There is an increase in intensity as because before the planet, this is suppose another star. If the star was not inside, not in my point, but when it was not here, the intensity was due to that background star only, that yellow one. So whenever another
correct.
star is coming in front, that intensity is that I am getting, and also that of the previous one due to this lensing kind of gravitational lensing. So both of these add up to give this increase of brightness, as I suppose.
Okay, so here, okay, so I'll be honest, this diagram does not exactly do this technique justice, because so what we do is we are not exactly just looking at one star, right?
Mm-hmm.
We are looking at a huge patch of
Background.
very bright, yeah, we are looking at a really bright patch. So
Mm-hmm.
it's not just one star, there are some stars here, here, here. So what happens is that, like, since because of the bending of light because of gravity,
Mm-hmm.
what essentially would happen is, if you have a star here, then this star would essentially drive the rays of light towards itself
Yeah.
and direct it towards us,
Mm-hmm. Mm-hmm.
right?
I
So it's
understand.
not just one star, it's actually a couple of stars.
Yeah.
So if this was a single star, you would get a very smooth data. As the
Yeah.
star is passing in front of that bright background, you just get a like increase in brightness over time, and then it goes away.
Okay.
It's fast, as
Mm-hmm.
simple as that. But if you have a planetary companion, what is going to happen is, first, as the star is going to move in front of that particular bright background,
Uh-huh.
you will get a raise in intensity. It will increase, and then as the star is moving away again, it will start to decrease. But now the planet is here. The
Mm-hmm.
planet is also having some gravitational pull of its own.
Exactly.
Now
Exactly.
the planet is going to pull some of that light, and that is why you have the slight blip again.
Mm-hmm.
And then as the entire system moves away, it dims down.
Okay, now if I can guess, if the planet is
Hmm.
accompanied by a moon, then there would be
Hmm.
two blips.
Yes, that is
Okay.
what
Mhm.
we sort of expect.
Okay.
That is what
Okay.
we
Okay.
would look for essentially.
Okay. Okay. I
So
get
that
it.
is why people are trying to probe it into a much finer,
More finer details.
yeah,
Yeah.
we
And
are trying to probe
obviously,
it in a higher resolution.
and 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 since the moon would be even less massive than the planet, then we will have that tip would be also that blip will be very much small compared to this one, second one.
Precisely. So like
Okay.
that is the challenge as of now. That so far we do not have a single, we like absolutely do not have a single detection of exomoon whatsoever.
Okay.
And the only, and like so far what people are planning, the way they think we can discover exomoons
Mm-hmm.
is through this particular method. But
Okay.
I'm not sure how good the ground based telescopes would be for this particular detection, since it's very sensitive.
Mm-hmm.
So some research groups, or like some exoplanet research groups, what they are planning is that once the Nancy Grace Roman Space Telescope will be launched into space,
Mm-hmm.
they will essentially use that space telescope to point it towards the Milky Way patch
Mm-hmm.
and see if they can get some exomoon detections.
That's a very interesting. Very interesting. Thank you. Please
Yes.
continue.
Yeah.
আচ্ছা টিসিয়া,
Uh,
হ্যাঁ, হ্যালো টিসিয়া, হ্যাঁ টিসিয়া, আমাকে একটু বেরোতে হবে কারণ আমার ওই অবজারভেশন চলছে, তো একটু নাইটে থাকতে হবে আর
oh,
কি।
okay.
হ্যাঁ, সো পার্থ স্যার,
হ্যাঁ হ্যাঁ আমি
এভরিবডি
আছি
ইজ,
আমি আছি
আমি, হ্যাঁ তুমি একটু থেকো, আমি একটু যাই, আমি
আচ্ছা
আবার কালকে জয়েন করছি। ওয়ান্ডারফুল
ওকে
টক
ওকে
হচ্ছে, এবং
হুম
কন্টিনিউ করো। হ্যাঁ,
ওকে
Thank
ওকে
you, sir.
ওকে ওকে গৌরব
ওকে
Yeah,
ওকে,
okay.
হ্যাঁ,
Bye bye.
বাই
See you.
বাই,
বাই
হ্যাঁ,
See you.
সি ইউ।
All right. Okay, so moving on with the microlensing, the next way of detecting exoplanets, which we have, is direct imaging. And when I say direct imaging, I actually mean you just look at the exoplanets. It's there. Just look. As simple as that. And this is one of the things which my professor as well is working on. It's the Scales project, which will be essentially a part of the Keck telescope in Hawaii. And once you it's essentially an add-on to it. It's called Slicer Combined Area of Lenslets for Exoplanet Search. You can find some of the papers on the internet as well. And so the entire motive behind the direct imaging technique is to somehow make the exoplanets come into light. So now, okay, I showed you the visual already. So can someone tell me that, okay, why do we first, someone tell me, why do we not see exoplanets to begin with around stars? Whenever we can just observe a star, and if there are exoplanets around it, we should be just able to see them with our eyes, or I mean the CCD detectors or telescopes. We can just point the telescope at some star and be like, oh, look, exoplanets are there, we can see them. But that does not happen. If that were the case, we would have found exoplanets long back, and direct imaging would have been one of the first ways we found exoplanets. So that does not happen. Question is why? Can someone quickly answer? Anyone?
Can you please repeat the question?
So the question is, let's say you point a telescope towards a star, and you can just expect to see the exoplanets there, right? You can just observe them. Simple. You point at a telescope, you look at exoplanets. As simple as that. But that does not happen. Why? That is the question. That's it. Okay, I'll ask it in this way. Why do you not see stars during the daytime? This is a much simpler question. Why do you not see stars during daytime? Come on, quickly, who can
During
answer?
the light noise of sun.
Yes, because of the sunlight, because sun is too bright. When can you see stars during daytime? Trick question. When can you actually see stars during the daytime when the sun is up?
Solar
Solar
eclipse.
eclipse.
Yes? Yes, precisely. A solar eclipse. So that is precisely the concept behind direct imaging. Good resolution, like really good resolution, and block the starlight. Can you see this particular black patch here? This is actually the star. And all of these things you see moving around here, these are the exoplanets around it. And as you can see, this has been taken over a couple of years. And so generally what happens is that since direct imaging is you looking at the exoplanets directly, you find long period planets. And again, you can see the planets directly with your telescopes, which also means that you have a very precise idea of how they are moving, how far they are from the stars, and what essentially how their orbital dynamics is going to be in the entire system. So if anyone wants to
Does it mean
challenge that,
does it mean that the star is blocked by another one so that it is completely
no, no,
darkened?
no,
So
no, no,
why
no.
the
So
star is why it is
yeah,
in
we
black?
block it. We block it,
Oh, we
or we
block it.
block it on all sides. Yes,
Okay, okay, okay. That's
we
interesting.
put a mask on the star in
Mm-hmm.
the telescope itself. So
Okay.
during the observation itself, we
Mm.
put a mask on the star,
Huh?
and so it's called a coronagraph or a star
Okay.
shade
Okay.
in popular terms. So
Mm.
we basically block out the starlight, and the moment we block out the starlight, the exoplanets can be seen shining in the darkness. As simple as that. It's the same idea we get from an eclipse.
Okay. Okay. I understand.
Yes.
Understand.
Okay. So now let me slowly go towards the end of this talk, and give you some statistics, and also let us begin with this particular thing at hand. So back in 2020, I was really interested in exoplanets and stuff. So I also started researching on exoplanets, like, okay, what are their detection methods? How do we observe them? What are the statistics? So on and so forth. And so this data that you see right now, it's taken from the NASA Exoplanet Archive, and this was taken back in 2020. This was the data back in 2020. How many, can anyone guess how many exoplanets were discovered back in 2020? Like up till that time? A rough guess, anyone? You can quickly type it out in the comments. You can just add these numbers up.
500.
Sorry?
4,000 4,000 approximately.
Yeah, correct.
Hmm.
4,000 roughly. So back then in 2020, there were around 4,000 exoplanets that were detected. And out of these 4,000 exoplanet detections, you had most of them detected through this transit, and then you had some detected through the radial velocity, obviously. Then you had gravitational microlensing here, you had direct imaging, and you had just one exoplanet detected through astrometry. Astrometry is simple. If you, let's say, have three background stars here, 1, 2, 3, and if you see some star wobbling around with the help of these background stars, so you measure the distance from here to here, you measure the distance from here to here, you measure the distance from here to here. You essentially use three stars to pinpoint a coordinate system of your own, and then with that you observe that this particular planet is wobbling. That is basically what astrometry means. It's wobbling, it's periodic, hence there is a planet. And then you can, like, depending on what your resolution is, you can measure the wobble and essentially put on constraints and do your calculations to figure out, therefore, what is the mass of the planet again. So it's kind of a variation on radial velocity method when the entire system is essentially flat. It's facing you like this. The planet is going round and round like this. Okay, so this was the condition back in 2020. This is now. See the stark difference? This is now. We are edging towards 6,000 exoplanet detections. And so just for a quick recap, the first exoplanet was discovered in the year 1995. Ever since 1995, it took us 25 years to discover around 4,000 exoplanets. And it took us just 5 years from then to discover in total 6,000 exoplanets. It took us 5 years to discover roughly 2,000 exoplanets more, adding on to what we already had. And on top of that, we have made some controversial tags. We have made many more exoplanet candidates which are yet to be confirmed. We are still essentially waiting on some demographics. Some observations are yet to come. And as of now, we are edging quite close towards 6,000 exoplanets. And once we hit that mark, we will then again try to probe further and find more exoplanets. So this is going to go on for the next couple of decades, to be honest. And so this is the statistics now. We have some 1,000 planets from radial velocity, some 4,000 planets from transit alone. And the stark difference being we have this many ways of detecting exoplanets today. Just this many. We can detect exoplanets in so many different ways today because of the amount of work which scientists have put forward in this past couple of years. That is how rapidly this entire field is growing. And now, just some light statistics where I essentially ask you to slowly focus your attention towards the fact that our solar system is actually pretty unique in some sense. So we do not know whether it's really unique or if it's because of the biases that we have due to exoplanet transit, because of exoplanet detections, like as in we are limited by certain factors which allow us to only detect some fraction of planets and not detect some others. We do not know whether it's that or whether it actually is the case, but apparently so far, after roughly 6,000 exoplanet detections around our sun or within our galactic neighborhood, we see that all the sorry let me switch to a laser point. Yeah, we see that most of these planets within the solar system are actually outliers. They don't really fit into the majority of the exoplanets that we have discovered. So now let me quickly come across one of the questions which one of you were asking, like what is the drawback of the first method? So the drawback of the radial velocity method is it does not allow you to detect small planets, because small planets will not tug strongly enough at the star. And let's say you do measure some wobble around the star, but your error is going to be roughly equal to whatever you have measured. So you do not have any way of saying that that really is a planet. So that is a huge drawback of the first method, that you cannot really probe into small planets. It's very difficult for you to probe towards Earth-like planets, and the only planets you can comfortably detect with radial velocity are hot Jupiters or giant planets. Those are the only planets that you can actually comfortably detect around these stars. You can also detect Neptunes or, in some cases, super Earths, but the detection does not have a good signal to noise ratio or a good confidence. And so this is planet mass and orbital period in days. So if you again notice, you have high mass, you have, so essentially we have detected massive planets with high orbital periods with imaging technique, and most of the short orbital periods are detected by the transit. And then you have this entire patch here which have been detected by radial velocity. And like as I said, radial velocity will only allow you to detect larger planets, hence the crowd here is more. And transit allows you to detect mostly planets which have a very short orbital period around the stars. Because let's say a planet like Jupiter, or rather a planet like Neptune, if the planet itself takes some 50 years or 100 years to go around this star, then you essentially need 3 transits to confirm that it truly is a planet. And if that is the case, you need to wait 300 years for a transit observation to be confirmed. By then, we will just discover other methods to discover exoplanets altogether.
এই
So
টিস্যু,
that,
এটা তো দেখে মনে হচ্ছে কিছুদিনের মধ্যে তোমরা একটা এই এক্সোপ্ল্যানেটস একটা এইচআর ডায়াগ্রাম টাইপের বানিয়ে ফেলবে, ছবি দেখে লাগছে যেটা।
হ্যাঁ, মোটামুটি মানে ওইদিকেই যাচ্ছে
হ্যাঁ,
জিনিসটা।
ওদিকেই যাচ্ছে মনে হচ্ছে। হ্যাঁ,
হ্যাঁ, এইটার ডায়াগ্রাম না হলেও আর কি,
হ্যাঁ,
একটা,
কাছাকাছি কিছু একটা
হ্যাঁ
প্যাটার্ন হয়তো পাওয়া যাবে, হোপ সো।
হ্যাঁ হতে পারে। বাট তো এখানে আমি আরেকটা জিনিসও আসবো এরপর। তো ওটা মোস্টলি আমি পরের দিন কালকে কভার করব,
হ্যাঁ,
which is that exoplanets are mostly detected around low mass stars, and
ওকে।
there is a very good reason for that. And we will also discuss in the next class that uh, the fact that they are discovered around low mass stars also gives us the opportunity to actually probe into life and why that is important. So
এক্স্যাক্টলি।
like, and all of that will be discussed tomorrow.
বড়
Okay.
গুড, ভেরি গুড।
So, so far these are the statistics, and as I was saying, density is important. So here you have density of iron indicated by this line, density of magnesium silicate indicated by this line here, and then you have water line, density of water. This is the line that indicates the density of water. So now you can understand that Uranus and Neptune are here. They are less denser than water. Those which are denser than water, Earth and Venus, they are roughly around here. And then you have Mercury right around here, which is a very small planet to begin with. And then you can see that the most of the planets which we actually have detected are either Neptunians or gas giants, and gas giants could not even fit within this particular graph. Jupiter is somewhere over here because everything is in Earth mass and Earth radius. So Jupiter is somewhere off in the corner. It could not even be fit into the same graph. And so this is why I essentially used Jupiter radius and Jupiter mass to show you two things. One is, can you see this line going here? Can anyone try and guess what this line is? I taught this to you today. It's a relation. What relation did I teach you that allows you to convert mass to radius, radius to mass for a planet? This particular line is an artifact of that. None of these planets exactly have both their mass and radius measured, but they have one of them measured. So can anyone remember what that relationship was called?
I just chain something, CHN kind
Yes.
of.
Yes, precisely that. So this particular line that you see here, this is an artifact of the Chen-Kipping relations.
Yeah.
And then you have comparatively lower density lower density planets, higher density planets here, and you have lower density planets here, which have, obviously, now since it's in the scale of Jupiter, mass and radius both are high, but the radius takes over the mass, and essentially the density drops down. So here you have the regime of massive planets, and here you have the regime of smaller planets, terrestrial or Earth-like planets. And then finally, the very famous plot, which every professor or scientist who is going to give a talk on exoplanet is going to use, at least for the next couple of decades, is the fact that we have discovered so many exoplanets, and the entire curve of detecting exoplanets is just increasing exponentially at this point, as I pointed out earlier. So our aim is now to essentially reach this 6,000 mark. We are very close. It's 5,800 something. And just a couple of months back, when I finished my paper, I wrote 5,500 plus. Now it's 5,800 plus. So it's going on very rapidly. And so that's more or less about it. That was the statistics. And as a final thoughts, I just wanted you to think on these points for a moment, because this is essentially what we will attempt to cover in the next class tomorrow. So as of now, there are roughly 6,000 exoplanets discovered so far, 5,879-ish something, last time I checked. And it is estimated that there might be billions of planets in the Milky Way alone. So Milky Way itself has some hundreds of billions of stars itself. And what we predict is that at least so nearly all of these stars will have at least 1 to 2 planets, which means there are probably more planets in the Milky Way alone than there are stars. Detecting them is a huge challenge, but the estimation is that we have billions of planets in our galaxy, and F, G, K, and M type stars are also the stars which would essentially populate the galaxy the most. So even in my research, I saw that obviously M-type stars are the most popular stars which you can find, at least within the solar, like around the sun or the solar neighborhood. Up till, let's say, about a couple of kiloparsecs, you will find that it's just populated with F, G, K, and M-type stars, small stars, and obviously there is a good reason for that, why that is happening. And we will discuss all of this tomorrow. And so the
So there
final
is a question. Spandan has some question regarding the data.
regarding the
Data. Data.
In the first data sheet where you have shown the radius versus mass, I guess that dotted lines, connected
yeah.
dotted lines.
Hmm.
This one, no, previous one.
This one.
Yeah.
Hmm.
Here in the last section, I see that at same radius there are two type of mass densities, right?
At same radius, okay, so at same radius there are two types of mass, yeah. Okay. Correct.
What does it suggest?
Oh, okay. In that sense, okay, good question. Okay, so what would you think that it suggests? So one thing I can tell you is that the points which you see scattered over here, measured mass and these have measured mass and radiuses. Okay. So now, for example, let's pick this particular line. So this has the same radius, but a really high mass. So this essentially points towards something very interesting, actually. And so as you can see here, this is one Jupiter mass, right? Sorry, this is one Jupiter radius. And this is roughly uh, zero point 0.3 Jupiter radius-ish. So which means it's roughly 0.3 times the radius of Jupiter, and Earth is roughly so Earth is roughly zero point 0.1 Jupiter mass. So Earth would be roughly somewhere around here. It's zero point 0.1 Jupiter mass, and it's so 300 Earths would make up one Jupiter mass. 300 Earth masses is one Jupiter mass, and 10 Earth masses is one. Sorry, 10 Earth radii is one Jupiter radius, roughly. So these planets here, or rather, let me point towards these ones specifically. Hmm. These now slowly go towards the regime which I did not discuss today, which is brown dwarfs. Brown dwarfs are these really dense, huge, dense, dead stars, you can say, but they are, in a sense, neither stars nor planets. Now, I understand it does not make such that much of a sense as such, but brown dwarfs are essentially those conditions where you do not exactly form a planet like Jupiter or any such thing, but at the same time you lose your potential to fuse hydrogen, and hence you do not become a star. So that is the area of brown dwarfs, and there are actually many you know many interesting areas in this portion where you have things like the Fulton gap, which is a radius gap, which I would rather implore you to figure out what or find out what the Fulton gap is. And then you have this entire regime of radius where you have the brown dwarf desert, where you do not see any planet for a certain extent, like for a certain expanse, and you see that these two places have essentially clumped together, right? And then how these things are all sparsed out. So there are many such cases where you will have uh, you know things which have tried to become a star, could not, from one sort of going towards becoming a planet but could not, and then stuck as something called a brown dwarf. And then we are yet to discover some other types of planets as well that sort of fills the gap between Neptune and Jupiter as well. So, to answer your question in brief, it suggests that we have planets of varying densities. So, even if you have the same radius, if the mass is high enough, it means that it's a really dense object, and it's a really dense planet. But that does not suggest that that particular planet is Earth-like or anything. What it rather suggests is that if it's that massive, it probably is going to shift towards a brown dwarf, because if it were Earth-like terrestrial planets do not go beyond this regime roughly. And even though you can see some detections here which are small, which have Earth-like radius, but they are sort of, how much? This is one Jupiter mass, yeah, but they are more massive than Jupiter. So these now slowly fall into that regime of compact objects and stuff, not compact stars, as in it. I'm not talking about white dwarfs and stuff, but yeah, more towards the regime of brown dwarfs. Does that answer your question?
স্পন্দন বোঝা গেছে? স্পন্দন বোঝা গেছে?
Spandana?
হ্যাঁ স্যার, বুঝতে পেরেছি।
আচ্ছা,
Okay,
Tisha,
perfect.
there was a question by Aditi.
Hmm.
She was asking that what classifies as life in this context: single-celled organisms, multi-celled organisms, or something entirely different?
Ah, right. So, lack of life on exoplanets, right?
Yeah.
So, let me come back to the last slide in that case. Oops, sorry. This was sort of an extra. Uh, so, that is what I sort of wanted to leave you with, which is, so your question specifically is what classifies as life in this context, right? So, that's the thing. We have no idea, to be honest. Like, we do not have absolutely any idea of on what classifies as life, in the sense that we do not know how life elsewhere might be. But sorry, not might be, what life elsewhere is. But we can have some idea of how life elsewhere might be from whatever we observe on Earth. So yes, your speculation on that it can be single-celled organisms, it can be multi-celled organisms. So if it somehow replicates, if it shows any form of locomotion, which is a self-motivated locomotion, or anything resembling the life that you see on Earth, basically anything which you have read as the definition of life in your biology books. If it is anything of that sort, if it is, let's say, undergoing some chemical reaction, specifically if it's self-replicating, then we will suggest, then it will suggest that yes, that probably is life. So essentially, I wanted to leave you with the Fermi paradox, which says that, like, okay, so oh, just 1 minute.
Tisha, there is a problem with your audio video. It again gets solved. Hello. Tishu, I think your internet connection is unstable right at this moment. Can you hear me? Hello. Your audio is, I think,
Yeah,
something
extremely
happened.
sorry. My laptop switched off.
Okay, no problem, no problem. So,
Hello.
yeah, I can hear you. We
Yeah.
can hear you all.
Hmm.
So, is that for today? Okay.
Yeah.
Would you continue tomorrow? This is a very
Yeah.
nice and
Just
interesting talk. Do
yeah.
you want to add something more?
No, no. So, like, just to complete finish quickly on what I was like cut off from. So, like that is essentially the Fermi's paradox. That even though you have so many worlds, so much probability that life elsewhere to exist,
Hmm.
even though you have so many planets and the probability of exomoons like orbiting around gas giants and stuff,
Hmm.
then even after all this, where is everyone? Why do we see not a single evidence of life elsewhere in the universe other than Earth?
Hmm.
So I leave you with the Fermi's paradox. And thank
Okay.
you.
Okay, I understand. So thank you, Tisho, for this wonderful lecture today. I hope we would have more audience tomorrow. I would try to upload this to the YouTube channel, and Gaurav will post you the link so that you can also share the video. Okay. So good night, everyone. Good night, Tisho. See you tomorrow at the same time, 7:30
Yeah,
p.m. Okay. Thank you.
yeah. Thank you for having me.
Thank you.
Yes, thank you.